Hello, students of science. In this video, we're going to talk about the colligative properties of solutions. So, colligative properties is a kind of funky, weird word. Basically, it means it's a property that's affected by the concentration of a particle, but not the identity. That's a weird concept. I'll go into that more in a moment here. A non-volatile solute, regardless of the compound, is going to change the vapor pressure of a solution. So here I have a pure, here I have something with solute. It's going to change how everything is going to work. For example, freezing point is going to be decreased and boiling point is going to be increased. Both of those are going to be changed when you add a compound to it. And once again, it doesn't matter what the compound is. Salt, magnesium chloride, sodium nitrate. It doesn't really matter. You could walk into virtually any chemistry lab and just start pulling things off the shelf and assuming that they're non-volatile when you add them in. When you put them in water, the freezing point is going to go down and the boiling point is going to go up. So you could have where you're going to essentially be expanding our phase diagram here. Here's my pure solvent. Here it is when I start putting a solution in it. The liquid phase is increased. Salt water might be freezing at -2 degrees Celsius as opposed to 0. Salt water might be boiling at 104 degrees Celsius instead of 100 degrees Celsius for pure water. It's a colligative property because it doesn't matter what you're dissolving in. So here we have our phase diagram here with our triple point down there. Here we are, pure solvent. So thin to the liquid is just the green phase. When you add a compound, a non-volatile compound, it doesn't matter what it is. It's going to expand this liquid phase. Those are all going to be pushed out. It's now going to be freezing at a lower temperature. It's now going to be boiling at a higher temperature. It's going to be as a liquid more because of the things that are dissolved in solution. Freezing point of a 1 molal, not molar, molal non-electrolyte solution in water is going to be 1.86 degrees Celsius lower than the normal freezing point of water. The more stuff you dissolve in there, the lower you're going to be changing that freezing point. Where it was -5 degrees outside Celsius, it was cold, burr, all that water is going to be ice. However, when you put something on there, like a very concentrated solution, you might be pushing it out so that at -5 degrees Celsius, water can still be a liquid. This is why they're actually going to be putting those things on the road. So at -1.86 degrees Celsius, water might be freezing as opposed to 0. This is why they're putting the salt on the road. It's going to be depressing the freezing point, which is good if you're driving around. This means that water will stay liquid at lower temperatures. Water is a lot better to drive on than ice. A 2 mole solution is going to have a freezing point of -3.72. You can see that's 2 times my 1.86 degrees Celsius thing. If you put, salt on ice, that's what's going to be causing it to melt. It's going to go to the liquid portion. So the formula that you need to write down and remember, and we're going to be going through this, is delta TF equals KF times M times DF. Delta TF is the freezing point depression. This is going to be the change in the freezing point, not the freezing point. Very, very important. We're going to be measuring how much that freezing point is going to change. K sub F is going to be the mole freezing point constant. That's going to be different for each solvent. So the particular one for water is 1.86 degrees Celsius per mole concentration. And remember, this is different for each solvent, but it doesn't matter what the solute is. If you dissolve sodium chloride or potassium iodide or magnesium chloride or whatever, it's going to still be the same K sub F because it's still going to be in water. However, if we were to dissolve this into ethanol, we would have a different number here. But as long as we're using water, doesn't matter what we're going to be dissolving in it, we're going to be using this constant here. M is going to be the mole concentration. Remember, that's number of moles solute divided by kilogram of solvent. And finally, DF is going to be the dissociation factor. Roughly, that's going to be how many particles are in solution. If there's only going to be one particle in solution, like sucrose when it dissolves in water, it doesn't actually break apart, that would be 1. If it's sodium chloride, that would be 2 because the sodium and the chlorine would be separate. Remember, friends keep you from freezing. They lower your freezing point. Here's our non-volatile solutions, and there's our water. By the same token, boiling point is going to work like that. You're changing the vapor pressure by putting solute in there. This is also going to affect the boiling point. You have boiling water. If you pour salt in it, that's actually going to increase the boiling point. Stuff that might be boiling might stop boiling. It's still hot. It's just no longer changing to gas as rapidly. A 1 mole non-electrolyte solution is going to be 0.51 degrees Celsius higher than the boiling point of pure water, 100.51 versus 100 degrees Celsius. This is why they put things in your radiator that aren't just water. You don't want to use pure water. Pure water is going to boil at 100 degrees Celsius, and there's tons of things in an internal combustion engine that are way hotter than that. So what you're going to be doing is you're going to be dissolving something into that water, usually ethylene glycol or antifreeze. But it's not just anti-freeze, it's anti-boiling. It increases the boiling, so you can get super hot stuff, hotter than the boiling point of water, that's not actually turning to gas, which is bad if you've ever had a radiator overheat. Our equation is somewhat very similar. Delta T sub B equals K sub B times M times dF. So this one is going to be the change in the boiling point. Again, not the new boiling point, just what the existing boiling point is going to be changed by. K sub B is going to be our mole boiling point constant. Again, that's going to be different for each solvent. In this case, the K sub B of water is 0.51 degrees Celsius per mole concentration. M is the mole concentration, and dF is the dissociation factor. We're going to work some problems on those in just a second, but same idea as before, how many particles you have in solution, more or less. So, friends, in addition to preventing you from freezing, they also keep you cool, and it makes it harder for you to reach your boiling point.